Lesson 13.3, curved mirrors for Physics 30. Now, there are two types of mirrors, first of all, and the first one we're going to look at here is a concave mirror. It has a concave shape, and so the surface comes like this and will reflect. So the light coming in will all come towards one point. Now we've got a focus point, which is where all the light will actually come towards, and the center of curvature, which would be the actual radius. The focus is half of the center of curvature, mostly due to the fact that as light rebounds off, it bounces, the angle of incidence is equal to the angle of reflection, and so it's bouncing towards a point halfway between the mirror and the center. Now we also have a diverging mirror. This is the convex mirror, and that's as light comes in here, it's actually going to bounce outwards, spread apart. Again, we've got a center of curvature and the focus is halfway in between. But in cases of diverging rays, you have all the light bouncing as if it were coming from the focus. Now there's always three rays that we do for our diagrams. The first one is from the top of the object towards the lens parallel to the axis, and then reflecting through the focal point. Okay, so the way that would look, come across here and towards the focus. Second one, from the top of the object towards through the focal point, and then parallel. So, to the focal point, and then parallel to the axis. And third one is from the top of the object straight through to the center, and there's actually no change in the angle. So we can see here, the first one comes parallel, and then as if it were coming from the focus, or parallel and straight to the focus, depending on whether it is diverging or converging rays. Second one runs towards that focus and then parallel. If we were to extend this blue line here, we would see that it would run straight through the focus. So run straight through the focus and then parallel. The third one, straight through that center with no change in the angle. Now, here we're asked to describe the nature of the image in using ray diagrams. Now, there's three aspects that we're going to be looking at. The first one is whether or not this image is going to be upright or inverted. Upright meaning same direction, inverted meaning the opposite direction. We can have a reduced or enlarged. This means smaller than the original, and this would mean larger than the original. And the last one is real or virtual. Now, a real image will be where lines really meet, and it can be photographed. Virtual image is where lines seem to meet. Now, if we take a look at this previous one, because in the diverging case here, the light rays came, we wind up with this image here, but it would be virtual. We could not photograph that. So it can't be photographed. It can be seen, but it can't actually be photographed. So if we're to use the ray diagram, there's 3 rays, again, that we can use. The first one being parallel, and then runs through the focal point. Right? The second one runs through the focal point to the mirror, and then parallel. And the third one runs straight through to the center, which is actually twice the focal lengths. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the center would actually be here, and it would run straight through here with no change in angle. Now, these lines don't actually really meet anywhere, but if we were to continue them along, we see that the image where they seem to meet from is right here. Well, that's assuming this mirror actually was a little bit larger. And so what we've got here is an upright image, because it's sitting in the same direction as this one. It is enlarged because it's bigger, and it is virtual because the light rays really did not actually meet there. And so we call this a virtual image. Could not be actually photographed there. Let's take a look at this one. Again, we're going to run parallel and then through the focal point. But of course, light's not actually going to go through the mirror, and so it's bouncing off this way, but it seems to meet here. The second one runs through the focal point, and then once it hits, would run parallel. 6, 7, 8. And the third one runs straight through the center with no change in angle. Now, you probably guessed at this point that only 2 of those are actually needed. Third one is great for verification, but this here is also an upright image. It is reduced in size, and it is also virtual. Let's take a look at a third one. Runs parallel through the focal point. Second one runs through the focal point and parallel. And so we already can see that this will be an image that is upside down or inverted. It is a real image because the light rays are really meeting there. And it is, again, enlarged. Bigger than what we would have expected. Now, the diagram is not great, but again, we'd kind of be running something here. Either way, you still wind up with these qualities. Okay. Sometimes you're going to have to improvise a little bit and choose 2 because the third one is just not going to happen. Such as if this were actually, the object were actually placed at C or the focal point. So, real images is where rays meet. This is where rays have seemed to come from. Or seem to meet. Now, the focal length. We haven't talked about this, but when you're dealing with converging rays, you're going to use a positive focal length. When it's a diverging, you're going to use a negative focal length. HI and HO stands for height of the image object, and positive numbers represent upright. Negative numbers represent inverted. Excuse me. Now, objects are always positive. They're always upright to begin with. DI is the distance of the image, and positive represents a real image, where negative represents a virtual image. And again, all objects are placed at a real distance away. Now, if you take a look, the ones that are always going to produce upright, reduced virtual images are always when you're dealing with diverging rays. Now, diverging rays is specifically when you're dealing with the convex mirror, but we're using the term diverging so that we can keep the same rules when we're dealing with lenses a little bit later on. So when we take a look at some of these mathematics, M stands for the magnification. DO is the distance of the object. And again, that will be positive. H is the height of the actual object. And that will be positive as well. DI and DHI are the distance of the image and the height of the image. And that's where you can see the positives or negatives. And again, one thing that's missing here is the F4, which stands for the focal length. And again, positive is when we're dealing with converging rays, and negative is where we're dealing with diverging rays. There's two formulas on your formula sheet that has this. The first one is an M is equal to HI over HO equals negative DI over DO. And the second one has the focal length in it, which is 1 over DO plus 1 over DI. So let's take a look at where some of these mathematical problems would come into play. If we've got a 3 centimeter tall object, so this 3 centimeter tall object is the height of the object, 3 centimeters. Is placed 10 centimeters away in front, so that is DO is 10 centimeters. And because they're objects, they're both positive. In front of a concave mirror, concave mirrors, right, will have light converge. So the focal length that we've got here of 3 centimeters, we know is going to be a positive focal length, 3.0 centimeters, but positive. And again, you can see with those mathematics here that the positive and negatives is actually going to influence things quite a bit. We want to find the characteristics of this diagram, which means we need to find HI and we need to find DI. So given, first of all, with the two formulas, we've got both of the focal length and the distance of the object. We can find the distance of that image using 1 over F is equal to di plus do. Okay, we got 1 over 3 is equal to 1 over di plus 1 over distance of that object is 10. So we're looking for something that will have a di value. That didn't really make much sense. But you could do this where you transfer into decimals and solve using algebraic techniques. Personally, when everything here is in fractions, I like to actually use the fractions. And first thing we'll do is find that common denominator. Subtracting it from both sides, 3/30 from each side. Means that we've got 7 over 30 is equal to 1 over di. Lastly, that means 30 over 7 is equal to di, just inverting both of them, which gets you a value of 4.28 centimeters. But the main thing here, because we want to find the characteristics, is that this is positive. Positive di means that this is a real image. Next thing we're going to need to do is find the hi. Now, hi over ho is equal to negative di over do. We're looking for hi. Height of that object is 3 centimeters. That image is 4.28 centimeters, but we got to make sure we're remembering this negative sign. And distance is 10. So hi, multiplying both sides by 3, we find that hi is equal to negative 1.29 centimeters. Now, first of all, it is negative, which means that it is inverted. And second of all, that 3 centimeter object is now only 1.29 centimeters, which means it is also reduced in size. So this is a real inverted reduced image. We can draw a sketch here just to kind of verify. Now this is going to be just a rough sketch, obviously, but the focal length is 3, and we're placing it 10 centimeters away, so the object is sitting here. So running parallel and to the focus, and then running from the focus and then parallel, we see we've got a little image right there, and that's going to be our verification. Let's take a look at one more example. In this case, we've got 2.5 centimeter tall objects, so height of the object is 2.5 centimeters. Place 9 centimeters in front, so distance of that object is 9.0 centimeters. Has a focal length of 4.0 centimeters. Now that focal length, because this is convex, means it's a diverging rays, which means we're going to use negative 4.0 centimeters as our focal length. And again, we want to find the image. We're doing the same thing, except we've got this negative focal length. So 1 over f is equal to 1 over di plus 1 over do. 1 over negative 4 is equal to 1 over di plus 1 over 9. So that would get you 9 over 36, and that's negative, over 1 over di plus 4/36. Now you're going to need to subtract this from both sides, so you have negative 9 over 36 minus 4 over 36 is equal to 1 over di. Combining that, negative 13 over 36 is equal to 1 over di. Or di is equal to 36 over 13. Again, that's negative. Now, when you calculate that, you wind up with negative 2.77 centimeters. And because this is negative, what you're finding is that you have got a virtual image. Now, if you were really thinking about it, you probably remembered that always the small upright virtual image was caused with diverging rays, and we had diverging rays here. And so you might jump straight to the fact that, well, it's going to be upright and it's going to be smaller. We're going to just verify that mathematically using hi over ho is equal to negative di over do. Again, we're looking for hi over 2.5 is equal to negative 2.77, which actually turns everything positive. And do is still 9. Multiplying by 2.5 both sides. Winds up with a height of positive 0.77 centimeters. And because this is positive, we know that this is upright. And because it's smaller than the original image, we know that it is reduced in size. We can do a little diagram just to verify. Focal length being negative 4 centimeters, being 9 centimeters. It's going to come like this to the focal length, to the focal length, and then parallel. And there's our little upright virtual image. Okay, I do hope that helps. There are questions in your unit book to help, and if you do have any questions, please let me know.